Hey there, this is a battery. It's got two metal electrodes, one metal more active than the other metal. When you build a battery, you're going to basically design a battery around the electrodes that you're going to use. And you're going to choose two different metals that have different reduction potentials. In this case, zinc likes to be oxidized, and the copper ions in this solution like to be reduced. Now if I were to take this zinc and put it directly into the copper solution, the oxidation and reduction would take place in that one container. So what I do is I separate it. Take the zinc, which is going to be oxidized, and put it in one half cell, and I'm going to take the copper ions, which are going to be reduced, and put them in the other half cell. This way electrons are going to be dragged from the zinc over into the copper side, and I can make use of those electrons, power device, like there's a voltmeter here, as the electrons go from one electrode to another. What metals do you choose to make your electrodes, and how do you know which one is going to be the anode, the oxidized side, and how do you know which one's going to be the cathode, the reduced side? Well, in order to do that, we're going to put reference table J to the test. Reference table J is the metal activity series table. It tells you what metals are more active than other metals. Now, in general, metals that are higher up want to undergo oxidation. The metals that are further down, their ions undergo reduction, especially when you put the two together. We're going to be testing the relative activity of 4 different metals in this lab: copper, magnesium, zinc, and silver. Now, according to the reference tables, according to the metal activity table, it's reference table J, magnesium's got the highest ability to be oxidized, followed by zinc, followed by copper, followed by silver. So we're going to see if that actually holds true. We're going to react each of these metals with solutions containing ions of those metals. Now we're going to carry out 16 reactions here. How many should you expect to see take place? Well, metals have absolutely no reason to replace their own metal ions. You're not going to get anything out of it. So you shouldn't expect to see reactions where the metals react with their own ions. The net cell potential is going to end up being 0 volts, so there's absolutely no reason for these reactions to take place. Now you know how it works. Let's say magnesium is higher up than zinc is. Let's say magnesium is more active than zinc. That means magnesium should be able to replace zinc in a zinc compound, but that zinc should not be able to replace magnesium in a magnesium compound. So of the remaining 12, how many do you expect are going to take place? That's right, 6. We're going to take a look at that right now. The equipment you need for this lab includes a little container with 3 film canisters filled with samples of each of the 3 metals you're going to test, a test tube rack with pipettes with individual samples of the solutions containing the ions that we want to test, a pair of tweezers to move the metals onto a spot plate, and a template upon which you will place your spot plate. There will be a second spot plate standing by to show you what happened to the silver, as I don't have enough silver to go around. The first step in this lab is to get these metals into their spaces on the spot plate. Place a small amount of copper into each of the wells going along where it says Cu0. Then place a small quantity of magnesium into each of the well plates for magnesium. And then place a small quantity of zinc into each of the spots for zinc. You'll be able to tell if a reaction takes place because the color of the metal will change. Now to add the ions. Put enough of the copper solution into each of these spots to just cover the metal. Place enough of the magnesium solution into each of these plates to just cover the metal. Put enough zinc solution into these spots to just cover the metal. Place just enough silver solution into these spots to again just cover the metal. Then wait until the reactions proceed. And here is the example for silver. So here are the final results. Is there a reaction? Is there a reaction? Is there a reaction? Is there a reaction? For the magnesium, is there a reaction? Is there a reaction? Is there a reaction? Is there a reaction? For the zinc, is there a reaction? Is there a reaction? Are you getting tired of me asking this question? is there a reaction? And for the silver, did any of the silvers, in fact, react with the solution? Now that you've recorded your data by putting R for react or NR for not react on your data table, you can clean up your setup in the following manner. Fold up some paper towel, place it on top, turn it over, and give it a smack against the desk. This will knock the metals out of the spot plate, and then simply wash the spot plate out. The paper towel with the metals on it can simply be disposed of in the red disposal bin. Make sure that your setup is replaced back to the side of the room and you're all cleaned up.